Hello, everyone. Hope you're all doing well. Any questions on anything at all before we get going? All right. So the stuff that we're going to be talking about today goes along with section 7.4 in Hawks, which is about solving trig equations. So our whole goal here is to talk about basically the process that you would need to go through to be able to solve different types of trig equations that you might come across. So mainly, the big thing here to do is to make sure that you find all of the solutions that you have between 0 and 2 pi first, and then try to write down the general solution. So along those same lines, let's just look at the first problem here that I have on this worksheet, where we have sine of theta is equal to square root of 3 over 2. So the first thing I'm going to do... Oh, that was weird. That is a lot of there's a lot of feedback. So the first thing I'm going to do is I'm going to get sine of theta by itself. So just divide both sides by 2 to get root 3 over 2. So in this particular one, we know what angles give us a sine value that's square root of 3 over 2. We know that in between 0 and 2 pi, we know that theta is pi over 3, or theta is 2 pi over 3. So that was our first step here, was that we found, just to write this below here, we find all the solutions in the interval from 0 to 2 pi. Now, again, how did I find these? Well, first I see that the sine is positive, so I know I have my angle must be in quadrant 1 or quadrant 2, because the sine is positive. So I look for the angle in quadrant 1 or quadrant 2. That gives me root 3 over 2. Well, I know if it's root 3 over 2, the angle I started with must have been pi over 3 in quadrant 1. Must be 2 pi over 3 over here in quadrant 2. Okay. So that's our first step here, is to find all those solutions in 0 to 2 pi. Now, in some of the problems, that'll be all you have to do. You're just going to find all the solutions in 0 to 2 pi and be done. In other problems, it's going to ask you to write out a general solution. So the way we write out a general solution is using the period of the sine function, or the cosine, or whatever function you're talking about, to be able to write down all of the rest of the solutions. Remembering that once we rotate around 2 pi, if we think about drawing the picture, if I have pi over 3 over here, say this is pi over 3 up here, if I rotate all the way around again with 2 pi, I end up in the same spot again. So if I add 2 pi, I end up in the same spot. Or if I rotate around again and add 4 pi, I end up in the same spot. Or if I rotate around in reverse and subtract 2 pi, I end up in the same spot. So I would have the same sine value. So the way that we represent that with solutions is we write this as plus 2n pi. And this is where n is any integer. So any number with no decimal part, but it could be plus or minus. That's what we mean by an integer, no decimal part. And all this part is doing is just representing that we could rotate around as many times as we'd like and end up in the same spot. So if I add 2 pi, n would be 1. If I added or subtracted 2 pi, n would be negative 1. I could do that for either the pi over 3 or the 2 pi over 3. So this would be your final answer in that particular case. So let's see if we can find another one that looks like that. Let's see, I think there was another one that was down here. Let's look at number, well, it's almost exactly the same. Let's look at number 9 here, where we've got 2 sine x plus square root of 3 is equal to 0. So again, the first thing we're going to do in this particular case is get that sine of x by itself. So we will subtract the square root of 3 and then divide by 2 and then write a 2 in the wrong spot. Okay, so the first thing, again, I'm looking for x values so that when I take the sine of the x, I get negative root 3 over 2. So the first thing I'm going to think about is I have a negative sign here. So what quadrants am I looking for angles for? What quadrants am I interested in? 3 and 4, right? So I've got an angle down here, right? And an angle down here that I'm looking for. Okay, I see square root of 3 over 2 is the value that I'm interested in. Now, if I'm ignoring the negative sign, what angle do you know gives you a sine that's equal to root 3 over 2? What's one angle that you absolutely know for a fact gives you a sine value that's equal to root 3 over 2? I think it's 60, right? It's the pi over 3, right? Okay. Well, pi over 3 is up here in quadrant 1, but I know that that's my reference angle is the pi over 3. So what angles must be down here to give me negative root 3 over 2 then? If I'm in quadrant 3 and quadrant 4, what pi over 3 angles are down here? If I go all the way around to here, what's that? That's 180, or in radians, that's pi, right? And I have to add another pi over 3. So how far did we go? Yeah, so that's another 60, so that's a 4 pi over 3, right? We had to go 3 pi over 3 plus one more. Or so what's this one over here then? That must be the next one over, and it's 5 pi over 3, right? So the solutions that are in 0 to 2 pi are 4 pi over 3 and 5 pi over 3. So notice that's our first step in these, is to find all the solutions that are in 0 to 2 pi. And then the last piece that we do, again, is using the period of the function to write down all of the solutions. The period of the sine function is 2 pi. So we add in that 2n pi piece. So this is our general solution to that equation. Questions on that one? Let's see if we can find one more that looks like this one. I think there was one more down here. I'll do 17 later. Let's see. I think there was one with cosine down in here. Yeah, maybe I'm wrong. I thought there was another one like this one. Yeah, I'll just make one up instead. So let's say we had 2 cosine theta plus 1 is equal to 0. Do one with cosine here. So just like the previous ones that we did, I'm going to get cosine by itself. So we'll subtract the 1 over and divide by 2. So we're looking for angles that give us a cosine that's equal to negative 1/2. So since it's negative and we're looking at cosine, what quadrants are we looking in? Two and three, right? Over here. We're looking over here. And over here. Now again, if I ignore the negative, I'm just looking for a reference angle to start with. If I ignore the negative, what angle do you know has a cosine equal to a half? It's the 60, it's the pi over 3, right? So again, we're looking for those pi over 3 angles, but we're over here in quadrant 2 or quadrant 3, but it's a pi over 3 angle. We already just, in the previous example, we said this one was 4 pi over 3, right? What's the one in quadrant 2? What's the pi over 3 angle that's over in quadrant 2? Yeah, it's a 2 pi over 3, right? So this tells me that my theta has to be 2 pi over 3, or theta has to be 4 pi over 3. And then again, we use the period of the cosine function to write down the general solution. So we'll add in a 2n pi for those. So that would give us our general solution. Questions on that one? All right, let's start making things a little bit more complex. Let's go back up to the top here. And let's look at the second problem, where we have 3 secant squared x minus 4 is equal to 0. So much like what we did with all the previous problems we've done so far, let's see if we can get the secant all by itself right now. So we will add the 4 to both sides. Divide both sides by 3. And now I need to take the square root to get the theta, or excuse me, to get the secant theta all by itself. But we need to remember that when we take the square root of both sides, we always get plus or minus. So I'm going to get plus or minus. The square root of the top, it gives me a 2. So I'll get 2 over the square root of 3. Now again, just like in the previous problems, we're trying to find out the values of theta so that the secant of it gives me that plus or minus 2 over root 3. Now, we probably don't remember secant values off of the top of our heads very easily. So I'm going to rewrite this in terms of cosine, because I know that secant and cosine are reciprocals of each other. So this tells me the cosine has to be plus or minus square root of 3 over 2. Right, we're just taking the reciprocal here. So now it says it could be plus root 3 over 2 or minus root 3 over 2, which means that we're looking for an angle here in each of the 4 quadrants, because it says it could be a positive root 3 over 2, cosine's positive in quadrants 1 and 4, or it could be a negative root 3 over 2, and cosine's negative in quadrants 2 or 3. So I've got to look in 4 places for this one. But again, it's all based off the reference angle. So if I ignore the positive or negative, if I'm just concentrating on the square root of 3 over 2, what angle has a cosine equal to root 3 over 2? Yeah, pi over 6, right? So that's the one that's over here in quadrant 1, right? Oops. But we also have angles in quadrant 2, 3, and 4. So I need to find the other 3 angles, right? I've got, this is the one that's in quadrant 1. I need the ones that are in quadrants 2, 3, and 4. The one over here in quadrant 2 is going to be what? Well, all the way around to the side here is pi, which would be 6 pi over 6. So this one must be 5 pi over 6. This one must be 7 pi over 6. Because again, pi is 6 pi over 6. So we've got the one before it and the one after it. And then finally, this one over here must be 11 pi over 6. And the reason I know it's 11 pi over 6 is because if I go all the way around, I have at 2 pi, which is 12 pi over 6. So this one's one short of it. So then to finish this off, you get that theta is pi over 6, or 5 pi over 6, or 7 pi over 6, or 11 pi over 6. So we have 4 of them. And then again, we use the period of the function. In this case, cosine and secant, since they're reciprocals of each other, they both have a period of 2 pi. So to get the general solution, we just add multiples of 2 pi to each. So lots of solutions in that case. But again, notice that the process was exactly the same as the process we did in the other examples so far. We first found the solutions between 0 and 2 pi, and then we added multiples of 2 pi to get the general solution. So I don't remember if Hawkes calls it this or not, but when you do the solutions, I'll write it down here, the solutions between 0 and 2 pi are called the fundamental solutions. So we're looking for those first. We find those fundamental solutions first, and then use our knowledge of the period of the function to find the general solution. Any questions at all? Well, let's see if we can do one with tangent, because we haven't done one with tangent yet. So I'll just write it down here, just for a little bit extra room. Let's see if I wanted to do, let's say tangent of x, or let's say tangent squared of x is equal to 1. Just a straightforward one to start with. All right, so much like the previous problem, I want to get the tangent by itself. So I'll take the square root of both sides. When I take the square root of both sides, though, I get plus or minus 1. So I want to know where the tangent is equal to 1 and the tangent is equal to negative 1. Well, tell me one place where you know the tangent's equal to 1. So tangent is equal to 1 when the sine and the cosine are equal to each other. So when does that happen? I think it's pi over 4, right? 45 degrees gives you a tangent that's equal to 1. This would be the one that's in quadrant 1. We also have one that's in quadrant 2, which would be the 3 pi over 4. Now, I could go through and do the quadrant 3 and quadrant 4 as well. But in this particular case, since I'm working with tangent, tangent has a different period. The period of tangent is pi, not 2 pi, right? So notice for tangent, as soon as I find solutions between 0 and 2 pi, I'm done because I can add just multiples of pi rather than multiples of 2 pi. And again, the reason for the difference here is because we only need to find solutions here in 0 to pi because the period of tangent is pi. Okay, so once we find all the solutions in 0 to pi, we're done for tangent. We can just add multiples of pi rather than multiples of 2 pi because tangent repeats faster. We need to go all the way around from 0 to 2 pi for sine and cosine because it takes all the way around to 2 pi before sine and cosine start to repeat. But for tangent, you don't have to go all the way around to 0 to 2 pi. You can just do 0 to pi and then add multiples of pi, and you're done. So it makes it a little bit easier working with tangent from that perspective because I only have to look for angles in quadrant 1 or quadrant 2 to get my solutions from 0 to pi and then add in multiples of pi after that. Questions on that at all? Okay. Well, let's add a little bit more of a wrinkle in here. Let's look at number 5, where it asks for that. Say that again. Oh, I just get an echo again. That was weird. All right. So let's look at number 5 here, where we have 2 sine of 3 theta minus 1 is equal to 0. Now we're going to start this in the same exact way that we just started all the rest of them. All right, so the first thing we're going to do is we're going to add the 1 to the other side. And then we're going to divide by 2. It's exactly how we started off the previous problem. All right. Now, I see that I have a 3 theta in here, but I'm going to ignore that fact for the time being. I'm going to treat this like it's just an x or a y or whatever. This is the angle that I'm interested in. I'm just calling it 3 theta for the time being. All right, so I'm interested in angles that have a sine equal to a half. Well, again, in this particular case, we're looking in quadrant 1 or quadrant 2. One angle that has a sine that's equal to a half is pi over 6. That's the one that's in quadrant 1. So the one over in quadrant 2 is going to be 5 pi over 6. Now, in the previous problems, I would have just written theta equals pi over 6 or theta equals 5 pi over 6. But in this case, the inside of the function, the argument of the function, is 3 theta, not just a theta. So I'm going to write 3 theta equals pi over 6 or 3 theta equals 5 pi over 6. Because that's the inside of my function right now. The inside of my function is 3 theta, not just a theta. So I'm writing 3 theta is pi over 6. 3 theta is 5 pi over 6. And then add in the multiples of 2 pi. Then this looks exactly like what we've done in the examples that we've done so far, right? We got the trig function by itself. We found out all of the angles, all of the fundamental solutions first, and then added multiples of 2 pi, so the ones that we've done for sine and cosine. This just now has one more step. I don't have theta by itself yet. So for the one more step, we're going to divide both sides by 3. So in the first one, we'll have theta is equal to pi over 18 plus 2n pi over 3. This is dividing everything by 3. Or theta is 5 pi over 18 plus 2n pi over 3. So that was the last step that we needed to do in this one, was just take this 3 and divide it to both sides. Questions on that one? Let's do another one like that one. Let's see if we can do the one right next door to it here for number 6. I'm going to erase some of the stuff at the bottom if I need more room here. All right, so the first thing we notice in this one is that we already have the cosine is equal to -1/2. I'm not worried about this right now. I'm just treating it like it's an x or a y. I'm just treating the inside like it's just one big variable to start with, just like I did over here, right? I treated the 3 theta just like it was the variable. So we're doing this exactly like what we started the previous ones. Since I'm looking for where the cosine is negative, what quadrants are we interested in? Yeah, the 2 and the 3, right? So over here and over here. Then I think we've had one like this before where we said the cosine was -1/2. We had 2 pi over 3 and we had 4 pi over 3. Again, we know that the cosine of pi over 3 is 1/2, so we're looking for those pi over 3 angles that are over in quadrants 2 and quadrant 3. So just like what we did in the previous one, we will say that 2 theta minus pi over 3, whatever is on the inside has to be 2 pi over 3, or the 2 theta minus pi over 3 has to be 4 pi over 3. Notice all we're doing is treating the inside like it's the variable, like we've done in the previous problems. Same concept. Then we're going to add in our multiples of 2 pi. So that process is exactly like the process that we've been doing in the previous problems, right? Just taking the inside and setting it equal to the angles that we found and adding in our multiples of 2 pi. Now we just need to solve for theta. So to solve for theta, to get theta by itself, I need to add pi over 3 to both sides. In both equations here, we're going to need to add pi over 3 to both sides. So if I add pi over 3 over here, I just get pi plus 2n pi. And if we add pi over 3 in the second one, we get 5 pi over 3 plus 2n pi. And then for our last step here, we'll divide the equations by 2 to get pi over 2 plus n pi, or 5 pi over 6 plus n pi. So again, notice I'm focusing on the strategy here. The strategy is to first get what the angle has to, whatever this is on the inside, figuring out those angles first, and then getting the variable that's on the inside by itself. So notice that our first strategy is to get those angles, and then the second part is to get what the variable has to be. Questions on that one? By the way, my plan is for today and for Wednesday is just to do practice problems and make sure that we understand how this is working before I set you off on a take-home quiz or anything along those lines. So that's what I'm going to be doing, is solving these types of equations. We'll have to use our... I'm going to save the calculator part for Wednesday, because there'll be some... We'll have to get some calculator involved too. But right now I'm just interested in getting some equations solved. So let's do another type of one here. Let's look at number 4, and then I'm going to do number 3. Try to get some of this other stuff out of the way here. Oops, that was not what I wanted to do. Well, now you can see the solution. It erased that whole thing. Let me see if I can undo on here. Try to hide that. I want to go through it. I don't know if I can undo it or not. Let's see. Sorry about that. That was not my intent. There we go. That's what I wanted to see. Stop it. Okay, fine. I'll erase that other part. It wants to delete where I blocked it. This file had that I used, it had solutions on it too. I'm going to post the solutions to these on Moodle so you see them, but I don't want to go through that. I don't want you to see it right now as we're going through it. All right, so this one's a little, number 4 is a little bit different. We have, not only do we have a sine squared in here, but we also have a sine. So we're not going to be able to isolate the sine like we did in the previous problems, right? We only had a single term involving sine or cosine or tangent in the previous problem. So I'm not going to be able to isolate it like we did before. So we're going to have to use our knowledge of factoring to be able to solve this particular equation. That's how we typically solve quadratic equations anyway. Prior to this class, when you had an x squared and an x, you wouldn't try to isolate the x, you factored instead. So we're going to do the same thing here. Notice that both terms have a sine in it. So I'm going to factor out a sine theta. In the first term, when we factor out one of the sines, we're left with 2 sine of theta. And then in the second term, we're left with plus root 3. So we have sine of theta times 2 sine theta plus root 3. That's equal to 0. And now that we have a product equal to 0, just like we have in the past, in past classes, you can set each piece equal to 0. So in the first one, we get sine of theta is equal to 0. Or 2 sine of theta plus root 3 is equal to 0. And now notice that we've got equations just like what we've solved before. Right? These now look like equations that we just got done doing examples of. So let me get this one, the second equation. Let's get it, the sine of theta by itself first. If I subtract square root of 3 and then divide by 2, we get negative square root of 3 over 2. Let's do this second one first because it looks a lot like what we've been talking about from the previous examples. The sine is negative, so we're going to be looking in quadrants 3 and 4. The value here without the negative sign is root 3 over 2. So I know it's going to be a pi over 3 angle. And the pi... What was that? I'm sorry? I just didn't hear it. Does anybody have a question? One of them is 4 pi over 3. Exactly right. Good. What's the other one? So you got one that's, let me see if I can draw the picture here. The 4 pi over 3 is here. The other one would be over here. So that would be, which one? This one's, so we just need to add another pi over 3 to get to there. So this one's going to be 5 pi over 3. Just got to add another pi over 3 to it. And then we're going to put those multiples of 2 pi in here again. So that's for that one. So now we need to do the other one. So the second one's just asking for when is sine of theta equal to 0. So when is sine equal to 0? Tell me some angles that give you a 0 for the sine function. 0 does. What else works? Pi does, and 2 pi does, and so on down the line, right? So this one we can write as theta is equal to multiples of pi. And we can think of that, if we think about what the sine function looks like, what its graph looks like, remember it goes up, down, back up again, right? And everywhere it crosses the x-axis is where we would have a solution to this equation. So we've got negative 2 pi, negative pi, 0, pi, 2 pi, all of the multiples of pi, and that's exactly what this is written as, is all of the multiples of pi. So this that I'm circling here would be the solution to that equation. But notice again that for each of these parts, we was solved just like we were solving in the previous examples. So the only thing that was different in this particular problem versus the previous problems was the fact that we had to factor first. It's literally the only difference that we had, was that we had to do some factoring. Any questions on that one? Okay. So let's go to number 3 here, because this is another factoring one. So we've got 2 sine squared theta plus sine theta minus 1 equals 0. If this weren't sine theta and sine squared theta, if you had, say, 2x squared plus x minus 1 equals 0, if I think about this off to the side, I would want to try to factor this into 2 binomials. I would have a 2x and an x. Is the only way I'm going to be able to get an 2x squared. And then to get a minus 1, I have to have a plus and a minus. But I have to put it in the right spots to get a plus x in the middle. So I'm going to need a minus 1 here and a plus 1 there to be able to factor that. Well, this is the same type of factoring that you're going to be doing over here. The only thing I did here is I just replaced the sine of theta with an x. So the factoring here is going to be 2 sine of theta minus 1 times sine of theta plus 1 is equal to 0. And this is indicative of the type of factoring problems that you'll have to do for these, to be able to solve these types of equations, is being able to factor these types of quadratics. All right, so then just like what we did in the previous problem, we're going to set each piece equal to 0. So we have 2 sine of theta minus 1 is equal to 0, or sine of theta plus 1 is equal to 0. After we set each piece equal to 0, we solve it just like we've done every example so far. We isolate the trig function. So sine of theta equals 1/2, or sine of theta equals -1. So for this first one, the sine is positive. So we're looking in what quadrants? 1 and 2. And we're looking for when it's equal to 1/2. So the angle in quadrant 1 that gives you a sine that's equal to a half is what? Pi over... It's the other one. It's pi over 6, right? And then what's the one that's over in quadrant 2? I even have the pic. It's a 5 pi over 6. Good. Cool. And then for each of those, we would add multiples of 2 pi. And then for this one's a little bit different. We need to know when the sine hits -1. Well, on our graph, if we just look at it's probably easier to see this one on the graph. Remember, the lowest that the sine ever gets is -1. And where does that happen here? What value is this for where it gets down to -1? That is 3 pi over 2. Good. So this is going to be theta equals 3 pi over 2. And then I also need to add 2n pi to that. So all of these give us the solutions to our equation. Questions on that one? Let's see if we can do another one where we have to factor, where it may not look like we have to factor to start with. So let's look at number 7 here, where we have secant of theta minus 3 plus 2 cosine theta is equal to 0. So this one is hidden on us a little bit, that this one actually turns out to be a quadratic because it's written slightly differently. So this is an example of a type of problem where the first thing that you're going to want to do is get everything I can in terms of the same trig function. Now this one's not too hard to do in this particular example because I just need to make secant 1 over cosine. So now I have everything in terms of the same function just by making secant into 1 over cosine. This looks, I mean, none of us want to have to deal with fractions, okay? So I think the first thing that we want to do to help us out in this case is let's multiply both sides by cosine theta so that I get rid of the fraction. Well, on the right-hand side, I still have 0. When I take the 0 times the cosine theta, I still get 0. On the left-hand side, we need to distribute this cosine theta to all 3 terms. So when we do that, we get 1 minus 3 cosine theta plus 2 cosine squared theta. And notice what we've done by rewriting and multiplying by cosine theta is that we've converted that original equation into a quadratic, which looks a lot like the type of problem that we solved in the previous example that we did with sine. All right, so let's see if we can factor this thing. If we're going to get a 2 cosine squared theta, I need to use a 2 cosine theta and a cosine theta. And now I need a plus 1, but I also need a minus 3 cosine theta. So I need to use minus 1 in both cases. So that factors as 2 cosine theta minus 1 times cosine theta minus 1. And then do the same thing what we've just done in the previous problems. Set each part, each factor equal to 0. So we get 2 cosine theta minus 1 is 0, or cosine of theta is minus 1 is 0. Get the cosine isolated now. So we have cosine theta is equal to 1/2, or cosine theta is equal to 1. And now we got to figure out when that can happen. So cosine is positive. We're looking in quadrants. What? What quadrants are we looking for when cosine's positive? 1 and 4 again. And in quadrant 1, the angle will be pi over 3. So let's see if I can do this. Let's do this down here. So in quadrant 1, it will be pi over 3. In quadrant 4, it'll be 5 pi over 3. And then again, we add multiples of 2 pi. The last one here, we need to know when cosine is equal to 1. Think about the graph. I'll draw it off to the side over here. Cosine graph looks like this, right? Ooh, hey. Where is it up here at 1? 0. Good. So this would be theta is equal to 0. That's up here. And then it hits at 2 pi again, so it would be plus 2n pi. And usually we would just write that as theta equals 2n pi, rather than having the 0 plus in front of it. It doesn't hurt to have the 0 plus in it. I'm just saying we don't usually write it that way. So this then would be your solutions to that particular equation. Questions on that one? All right. I'm going to get solutions to all of these posted on Moodle for you so that you have them. And we're going to do more examples on Wednesday. There's still a few things that we need to talk about. We haven't used any trig identities yet to help us rewrite equations, so we're going to do that. And then there's also going to be some problems that pop up where you're going to need to use your calculator to find all the solutions. So we'll talk about that as well on Wednesday. So we'll get to that Wednesday. Like I said, I will get this posted on Moodle, and then tomorrow I'll probably post a couple of more videos just as examples, so that you can see the different types of equations that you might need to solve. So we'll do that next time. So have a good day, everybody.